Hi, everybody. So now we're going to use our knowledge of isomorphisms to prove some classification results, where we're going to show that if you know certain things about a group, then you know everything about it. So for example, we're going to prove that if a group is infinite and cyclic, then it's isomorphic to the integers. And if it's finite and cyclic, then it's isomorphic to Z mod n. And then after that, we're going to prove a very abstract classification result in which we prove that basically every group can be thought of as a group of permutations. And in particular, every finite group is a subgroup of a symmetric group on n elements for sufficiently large n. And this tells us that we can use what we know about permutations to think about very general types of groups. So let's start with our first classification result. Any infinite cyclic group is isomorphic to the integers. So here, remember, as always, but by the integers, I mean the integers with addition. And it is an infinite cyclic group because it's generated by 1. Right? You take positive and negative multiples of 1, you get all of the integers. And now what we're going to prove is that if G, so another way to state the proposition is suppose G is infinite and cyclic, then there is an isomorphism F from Z to G. And so how do we prove this? Well, we have to construct this isomorphism. And I think the way to think about it is that if G is infinite and cyclic, then it has a generator, G, little g, let's say. And what does it mean to say that your group is infinite and cyclic? Well, to say that it's cyclic means if you take this G and you take all positive and negative powers of it, then you get the whole group. So in other words, if G is cyclic, means that there is a generator in G so that, first of all, G is the collection G to the n for all n in Z, and all of these powers of G are different. Because if two of them were the same, then the group wouldn't be infinite anymore. I mean, if G to the 5th were, say, equal to G to the 20th, then that would mean that G to the 15th was equal to the identity, and that would mean that G had finite order, not infinite order. So if we look at this for a minute, we can see how to construct our isomorphism, because we can take Z to G by using this exponent. We define f of n to be G to the n. And first of all, this is an isomorphism because f of n1 plus n2 is G to the n1 plus n2, which is G to the n1, G to the n2, which is f of n1, f of n2. Accounting for the fact that I'm writing the group operation as multiplication in G and as addition in Z. So that's one property. The other property we need to check out is that this is actually bijective, but that's where we use this fact that the group is infinite cyclic, because suppose F, how do we show, first of all, that it's surjective? F is surjective because every G in G, let's call it G1 in G, is equal to some power of G, so f of m is G1. The fact that G is cyclic means every element is a power of G, and therefore if we have an element and we want to get it using this map, we take the power. And it's injective because Because if f1 equals f of n2, f of n1 equals f of n2, that tells us that f of n1 minus f of n2 equals 0. Or I guess I should write it, sorry, I should write it, this is in G. So this would mean that f of n1, f of n2 inverse equals the identity. And that would tell us that f of n1, f of minus n2 equals the identity, because f of n2, remember, is g to the n2. So f of minus n2 is g to the minus n2, which is g to the n2 inverse. So, and this is f of n1 minus n2 equals the identity. But this is g to the n1 minus n2 equals the identity. And the only way that can happen, the only power of g that can be the identity, is if n1 minus n2 is 0, because otherwise g would have finite order. And that would contradict the fact that the group was of infinite order. So we have a bijective map from the integers into G by sending 1 in Z to a generator in G. This is a really important construction. Whenever you have a cyclic group, an infinite cyclic group, if you take the group Z and you send 1 to the generator, you can think of your infinite cyclic group as like a copy of Z. And really what you're doing is you're just looking at the exponents that you need to raise the generator to get any particular element. Now we have a result about finite cyclic groups. If an infinite cyclic group is automatically isomorphic to Z, a finite cyclic group of order n is automatically isomorphic to Zn. And as we're going to see, the proof is quite similar. It's a little bit trickier, but let's suppose that G is finite cyclic of order n. And we need to find a function from Z mod n to G, which is an isomorphism. And so again, G is generated by some element G, little g. And so let's define f of f of A to be g to the A for A in Zn. Now we have to be a little bit careful here because an element of Zn isn't really a number. It's only a congruence class. And so I could choose a different representative for the congruence class. So for instance, if I were to take A and add a multiple of n to it, because I'm in Zn, this would represent the same congruence class as A. And so it better be the case that if I used a different representative for the congruence class, I better get the same answer for my function. And if you work this out, what you see is that you get g to the A times g to the n to the k. But g is cyclic of order n, and g is a generator. And if g is a generator of a cyclic group of order n, that is equivalent to saying that g to the n is the identity, but no smaller power of g is the identity. That's what it means for g to give you a generator group of order n. And so in particular, this is g to the A, and we see that if I happen to choose a different representative for the congruence class, I get the same element in G. And so the map, this is called, I mentioned this once before, it's called being well defined. So if I know a generator of G and I raise it to a power given by A, then if I choose a different congruence class, I get the same map. So I've proved now that I have a function, but if I want, and it has, I want to check that it has the isomorphism property and that it's bijective. So let's first check that it's bijective. So suppose it's not. Well, maybe there's two ways to go about it. Suppose it's not bijective. Or better yet, let's first show it is surjective. And for that, we use the fact that if G1 is in G, then because G1 is generated by little g, we know that G1 has to equal G to the I for some I. And we can choose I between 0 and n because it's a cyclic group of order n, so we know that G to the 0, G to the 1, dot, 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 up to G to the n minus 1 is all of G, because G to the n is going to take us back to the identity. And therefore, I see that if I take f of I, that's going to be G to the I, where I've now chosen this I, the congruence class of I in Zn. So that shows that I can get any power of G that I want in the range from 0 to n minus 1 by taking a representative from 0 to n minus 1 in Zn. If I want to show that it's injective, suppose that f of I equals f of j. Well, that would mean that G to the I equals G to the j, which would tell us that G to the I minus j is the identity. But G has order n. And the only way that a power of G can be the identity if G has order n is if n divides I minus j. The power has to be a multiple of the order of the element for this to be true. Otherwise, G would have smaller order and the group wouldn't be of order n. So the only way f of I can equal f of j is if n divides I minus j, and that's only if I is congruent to j mod n, which means that the class of I equals the class of j in Zn. So if f of I equals f of j, this implies that I equals j, and so the map is injective. And I guess finally we should check that the isomorphism property holds, and that's because f of I plus j is G to the I plus j, which is G to the I, G to the j, which is f of I, f of j. So the proof is very similar to the case where you have an infinite cyclic group, and you see that if you have a finite cyclic group of order n, it's necessarily isomorphic to Zn. And just to remind you, we worked this out for U of 7. We saw that U of 7 is cyclic of order 6, generated by 3, and that it was isomorphic to Z mod 6. But in fact, any cyclic group of order 6 is isomorphic to Z mod 6. Now we have a really general classification result. In the previous one, we showed only that a cyclic group of order n is isomorphic to Z mod n. This theorem says if you have a group, any group, the only assumption you make is that you have a group and it has a prime number of elements, then it has to be isomorphic to ZP. And the proof of this is that if you have a group of prime order, it's necessarily cyclic. So let's suppose G has P elements. And P is prime. So take an element in G, which is not equal to the identity, and we know that the order of G has to divide the number of elements in G, by Lagrange's theorem, which tells us that the order of G has to equal P because it can't be 1 because G is not the identity. And the only possible divisors of P are 1 and P. And that tells us that G has to be 1 G, G squared, up to G to the P minus 1, because these have to all be different, and G only has P elements, and we found P elements. So this is just a brief reminder of the fact that if you have a group with P elements, it's necessarily cyclic. But by the previous result, if you have a cyclic group with P elements, it's necessarily isomorphic to ZP. So since G is cyclic with P elements, G is isomorphic to Z mod P. So there's only one group up to isomorphism with prime order. There's only one group with 5 elements, one with 7, and that's a nice sort of classification result. It gets much more complicated if you, for instance, were to ask how many groups are there with P squared order, or if N has two prime divisors and so forth. But this is kind of a very beginning start on classifying groups.